Hello, everyone. This is going to be a recording that talks about how do we get information out of STAR-CCM Plus. Clearly, we were running simulations for a reason. We want to know something. How do we take that knowledge and take the information that will help us inform us of this knowledge and get it outside of STAR-CCM Plus so we can post-process it or put it in reports or presentations, etc. So, we have 4 folders on the main tree where this principally occurs. These are reports, monitors, plots, and scenes. Reports, monitors, and plots are closely related to each other. Scenes are kind of their own thing. They're all used to present and extract information, but they do it in different ways. We'll start with reports, monitors, and plots. So, reports, from the high level conceptual standpoint, do one thing. They define how you measure a thing. When you create a report, you will tell it what you want to measure, where you want to measure it, and how you want to measure it. It doesn't actually do the measurement unless you manually tell it to, but you define everything about your measurement. Monitors are devices that will go and make one of the measurements you defined. They go to a report and say, I'm going to record the value from this report. And they store it. So they take the measurement and they store the value. That's principally what a monitor does. Plots, it should surprise no one in particular, plots the data stored in monitors. And by plotting it, can give you insights into trends and patterns and things like that. It's literally just taking the data that exists in the monitor and plotting it. You can do the exact same thing in Excel or MATLAB or whatever other data processing tool you'd like outside of STAR-CCM Plus. But you could also do it inside of STAR-CCM Plus to see it in real time. Or maybe you just prefer its way of setting up plots. It's kind of user preference and it's already here, so in a lot of ways it's very simple. Um, but you don't have to plot things in STAR-CCM Plus. It just might be a lot more convenient depending on what you're doing. Now, reports, monitors, and plots are all for numeric data. That is, things that are represented by numbers or single numbers, or maybe at most a couple of numbers. They're not for things that represent data that varies across space. Anything that varies in 1, 2, or 3 dimensions really isn't well suited for reports, isn't well suited for monitors or plotting. Where we go for any data that is represented as it varies across space, we go to the scenes folder. What we're looking at right now is a scene. There are many different ways of configuring scenes. The sky's the limit. If you can think of a way to do it, you probably can do it. We'll circle back around to talking about scenes in detail a little bit later. For now, let's look at reports and see a little bit about how we can potentially set up some of these. Some of these have already been created. You can see drag, leading edge pitching moment, lift, center of pressure, Y center of pressure, etc. Okay, so let's go ahead and look at some of the different reports that we have to make. We already have some that exist, but let's look at some of the different types of things we can measure or the ways we can take measurements. So there are several folders here. The big one is flow/energy. There's some other very useful reports in these other folders. We'll get to those. So if we look at center of loads, I'm not going to go through all of these in super great detail, but I will go through a couple of the more relevant ones. So I'm going to go ahead and create a center of loads report, and we can see down here in properties, we get several options to change the properties of these. We can change the units. Where is the center? Is it in millimeters, micrometers, yards, kilometers, inches, feet, centimeters, angstroms? Pick your unit. Which coordinate system is it represented in? Is it the laboratory reference frame or some other coordinate system? Which direction? Are we concerned about the center of forces in the x direction, the y direction, the z direction? Which direction are we focused on? Are we focused on the pressure forces, the shear forces, or both? What is the reference pressure for this measurement? Should this reference point be located on the surface of the part, or should it be located on some reference plane? And last but not least, which type of or which part would we be looking at the center of forces on? In this case, probably the surface of our wing, but we could select any boundary that we have. And then we get a couple of options to change the units that it uses for calculation of force units and moment units and how it outputs them. But that's really all that we get for this. So hypothetically, let's just look at on the wing, what is the x location of the center of loads? Because it's 100, so this is in the x direction. It's all forces in meters in the laboratory coordinate system. And it thinks it's about 1/3 or 0.3 meters from 0, 0. So 0, 0 is a point that is not quite at the front of the airfoil, but it's up here vertically in line with the front of the airfoil, more or less. So it's about 1/3 of a meter away from that in the positive x direction. And this is a 1 meter chord airfoil, so that puts it a bit more than a quarter of the way back along the airfoil for the x location of the center of pressure in this particular case. We could also change this and say 0, 1, 0, look at the y location. Well, this is much closer to 0. It's a little bit below the y-axis, actually, or a little bit below the x-axis, rather, along the y-axis. And it's about 1.5 inches, give or take. A little bit less than that. Below the x-axis. That's the center of loads report. We could also just simply report forces. I already have a couple of these up. This is lift and drag, so we'll go ahead and look at these. Forces you report much in the same way. You tell it what forces do you want to report. Pressure and shear, only pressure. What direction do you want to measure the force in? Are you looking for forces in the x direction, the y direction, or a combination thereof? You could also look at forces along the 45-degree angle by looking at something that's not even a unit vector. It'll figure out the direction associated with that. And again, importantly, the part. What do you want to measure it on? So we're measuring forces. In this case, we're measuring force in the x direction, which happens to be drag. We're measuring pressure and shear forces on the wing in newtons. Could do the same thing with lift. The only difference is that lift is going to be in the y direction instead of the x direction. That is the only change to measure lift instead of drag in this case. We could measure force coefficients. Now this one gets a little bit tricky. because it has all the same definitions of forces for the most part, but it also has reference values. Remember, coefficients use reference velocities, reference areas, reference densities to calculate coefficient of lift, coefficient of drag, etc. STAR-CCM has no idea what is a reasonable value for these. It can't even hope to come up with a reasonable default value because everything is going to be so vastly different. So it just makes the assumption that the default is 1 for all of these. 1 kilogram per cubic meter, 1 meter per second, 1 square meter. Well, that's going to be wildly inaccurate in a lot of cases. Specifically, velocity is going to be wildly inaccurate in a lot of cases. So if you use a force coefficient report in STAR-CCM Plus, you better make damn sure to update your density, your velocity, and your area so it matches your reference area, your free stream velocity, your free stream density, and make sure those are correct. We're not going to talk in detail about heat exchangers. That's a little bit more advanced. We will talk about a couple more of these. We'll pass on heat transfer for now. We'll circle back around to that as needed. So mass averaged, and let me just pull this up here. Let's see here. There we go. Mass averaged. See, the help documentation is really helpful. If you don't remember a thing for sure, or you don't use a thing very often, you can look it up, and it probably has a pretty decent definition for it. So it's literally just taking the mass average of a quantity over part of the flow. So if you ask what is total pressure, it is total pressure based on the actual mass of the flow rather than any other quantity. So we can ask for, let's go with the mass average static pressure. Where could we ask for this? Well, notice we don't have as many options here. Let me blow up this menu a little bit. We can really only select the entire air volume because mass average has to exist as a volume. Right? It's not applied on a surface. It's in a volume because a mass exists in 3 dimensions. In 2 dimensions, it assumes that the depth is a unit depth, so 1 unit. So we can only really select the only pseudo 3-dimensional quantity we have, which is our entire region. So it's going to take the mass average static pressure everywhere here. Well, what's that going to be? It's probably going to be pretty damn close to 0. Oh, hey, look, it's 1.18 pascals. That's pretty darn close to 0 in my book. So this did exactly what we expected. It computed the mass average static pressure across this entire domain. We could have selected a smaller volume if we had one available. We don't, so it just computed it across the entire domain. Mass flow. We can ask it, what is the mass flow rate through a surface? Well, the only thing you really get to ask this is the units and what surface is it through. So if we ask for the mass flow rate through the wing, it says 0. Because this is a wall. Nothing's allowed to move through the surface of the wing. This is solid. So the mass flow rate through our wing, which is what I selected, is 0. Pretty self-explanatory. We could also, however, select boundaries through which surfaces can enter. Let's select the inlet. How much flow is entering? Oh, it's negative. That makes sense, though, because if you recall the definition of mass flow rate, a mass flow rate into a system is negative. And this is mass flow rate entering our control volume. In this case, a little bit over 1 point or 1 1/3 thousand kilograms per second is entering through this surface, which is a lot of air, but this is also a lot of area. We could also ask how much flow is leaving through the outlet. Let's see here. That would be the back surface. It's not going to be exactly the same because flow can leave through the top and bottom, but it should be similar. It's a little bit less. It's about 1 1/4 thousand kilograms per second is leaving, and it's positive this time, which tells you the flow is indeed leaving the system through the right-hand side. That is a mass flow report. We also have mass flow average. So what this will do is it will take the mass flow rate and take a quantity and average it against mass flow rate. Much in the same way you could do a mass average or an area average or a volume average. This is averaging a quantity based on mass flow rate. So we could take, let's see here. Mach number, let's say. Mass flow rate average Mach number through the inlet. So this is moving at about Mach 0.2, give or take. Which checks out. I think that's about right because our velocity is, on average, our free stream velocity is about 75 meters a second, which is about 1/5 of 330 or so, which is about the sea level speed of sound. So yeah, that is approximately correct. We're moving at a little bit over 20% of the speed of sound, approximately. Let's see here. We can also measure moments and moment coefficients in very much the same way as forces. The big difference is moments care not just about the axis that you're measuring the moment about. They care about where are you measuring it relative to. These moments have a moment arm. So the definition of this is basically the same. The axis takes the place of position, or excuse me, the axis takes the, not really, the axis is the direction that you're measuring the moment in, the direction you're measuring the moment about. The only difference is we need to add an origin. By default, it's 0, 0, 0, but we can plug in whatever origin we want to measure the moment about. So this has been set up in such a way that this airfoil is rotated about the quarter chord. So we could ask it for moment about the quarter chord of this airfoil, which means 0.25 meters from the front to the rear. And since it was rotated about that point, the quarter chord of this airfoil lies at exactly 0.2500. And as usual, we need to ask it, what surface do we want to measure these forces on? Most things in this simulation we're going to want to measure on the wing, so that is what we want to measure on it here. So it is going to be 204, almost 205, or closer to 205 Newton meters of moment about the quarter chord of this airfoil. Much in the same way we have a force coefficient, we also have a moment coefficient. Same thing, it takes the moment and non-dimensionalizes it. There is one additional reference value. We have a reference length as well, this reference radius. So remember, whenever you're doing coefficients, make sure your reference values are correct. But other than that, it's very similar to measuring forces or just moments. The only thing is you need to make sure the reference values are correct. Let's see here. I believe that's pretty much it for the important ones. There's obviously more. These are useful in cases. That said, those are the big ones you'll typically find yourself using in the flow and energy. Over here in metrics, you can measure things, and I'm not going to go through all of these in detail because it's somewhat self-explanatory in the mathematical sense, at least. So you can measure the frontal area. And this one I will actually demonstrate because it's kind of important. So we can measure the projected area in any direction. So if we're viewing, or sorry, if the view we're taking is with y up, so we have several different, let me see here. We have two different values. We have or three different values. We can select the units we want to measure this in. We have a property called view up and a property called normal. So view up generally means you're looking with this axis facing up towards the top of the screen. So right now we are indeed looking with Y up, and it has Y selected. The normal to what we're looking at is Z. So theoretically, this should, I believe, take the area of, well, really everything. Let's see here. If we select just our wing, what does it do? Oh, this is something very, very small. This is like 1,000th of a square meter. That doesn't seem very right. This thing's a meter long. And it's not very thick, but if this thing's a meter long and it's anything more than a millimeter thick, then it's probably bigger than that. So we just looked at the area effectively of this line. Or maybe the very first cell adjacent to this line. That's not making a whole lot of sense. We could measure the area of the entire domain. Notice how I just selected the big. It's a really subtle thing. I apologize. There are three little boxes here, and I just selected the big one only. So that's selecting a volume. If you select the little boxes, those are associated with surfaces. So if we look at this entire volume, it thinks that it's about 560 square meters. So about 16 meters tall by probably about 50 long, maybe slightly more than 50 long. Oh, wait, can I do math? 35 times, nope, that's about right. 16 times 36 is going to be pretty darn close. Yeah, minus a little bit of area for the wing itself. We're talking about 560-ish, 570 square meters. So if we asked for the entire volume, we do indeed get the area of this entire plane. Well, this isn't the most useful thing in the world because we're looking at it from the side. Most airplanes aren't measured from the side. You typically would look at either the frontal area or the top-down area. Well, if we wanted to look at the frontal area, the only difference is we would want to make this normal 100 instead. And this gives us 16 square meters. So if we measure from the top of this, oh wait, nope, we're still measuring the entire thing. So we basically measured 16 meters this way by 1 meter deep, which is why it's exactly 16. So we want to measure the frontal area of our wing instead. So we deselect all of this and just select our wing and run this again. and it thinks that it's 0.22 square meters. So if we measure this, we expect this to be about 0.22 tall. So I'm going to click here, and we see the delta y. I'm not the most accurate at clicking this in the world, but it thinks this is a little bit more than 0.2 meters tall, which is what we'd expect based on the measurement we just made of frontal area. We could also look at the top-down planform area. So imagine if we're looking from up here, vertically down, view up would be, well, really whatever we want it to be. It could be X, it could be Z, but we're going to say view up is X, and normal is going to be Y. And this says that the planform area of our wing is ever so slightly less than 1 square meter. Which makes sense. It's inclined a little bit because it's at an angle of attack, I believe 10 degrees. So the length front to back is slightly less than a meter, and it's assuming the depth into and out of the page is 1 meter. So you can use frontal area to measure all kinds of things related to areas, especially useful for perhaps automatically figuring out what some reference areas or reference chords are. You could also do various statistical activities on either surfaces or volumes. If you wanted to measure the average pressure on the surface of this wing, you could use a surface average. You wanted to measure how much, what is the standard deviation, or how uniform is the pressure over a surface, over the wing, for example, or over the inlet, or the top, outlet, bottom, whatever. You could use the surface metrics. You could do the same thing over the entire domain by using volume averages, volume standard deviations, volume uniformity measurements. We're not going to deal with the overset. That's a little bit more complicated. You could also have the system report how much memory is it using, what iteration is it on, how much CPU time is it taking per iteration, how much total time is it taking per iteration, how much total time has it taken so far, CPU and elapsed. You can, a little bit more complicated if you feel like getting into it a little bit more detail, you can use the user functions. You can take an integral over a surface, the integral over a volume. You can take the sum of a value over a surface or a volume, depending on what quantities you're talking about. You can find the minimum value for a thing, the maximum value for a thing, either in a volume or over a surface. Or the ultimate catch-all, if one of these does not fit your bill for whatever reason, you can make your own. You can use an expression. So if you make an expression, you'll see that it has a property called definition. With little ellipses, you get a window that looks like this. You can program your own. For example, I could say, I want something that's the, let's see here. What's a good one? Okay, I want the maximum value or I want the square root. Let's just try and keep things a little bit simple. Avoid overcomplicating things. Of the internal heat wall coefficient times the Mach number. That's a perfectly valid definition. It will have some dimensions that I'm not going to bother to. Actually, no, it's going to have no dimensions because coefficients and Mach number are both dimensionless. It didn't like that for some reason. Well, in any case, you can define your own expression mathematically. It will probably give you issues at some point. It will probably give you issues a lot of the time until you actually figure out what you're doing and why. But you can do math on all of these quantities, including other reports and things like that. Whether it's tensor based math, whether it's vector based math, magnitude, units, dot products, cross products, curls, divergence, etc. You can do all kinds of interesting math on all kinds of quantities um, to find out various things that might not be readily available. Most of the common things you can just make reports on and they're already programmed, but some of them aren't. And if they aren't, that's an expression. You make your own. You probably won't need to, but it's there if you need it. I'm going to go ahead and delete most of these because most of these are not particularly relevant. I didn't actually program them in a useful way. So we can make all of these reports. If you want to make a monitor from a report very easily, you can right-click on it and say create monitor from report. Or you can say create monitor and plot from report. So if I click on this really quickly here, we get a plot of the quarter chord pitching moment against the iteration of the simulation. We can also plot multiple things at once. If I want to plot lift and drag, we can say create monitor and plot from report. And it'll ask, do you want this on multiple plots or one plot? If I want to plot both of these on a single plot, you hit single plot, and let's run this a little bit. Oh, that stopped because the stopping criteria got hit. Let me turn that off. Well, it doesn't look like much because this has converged already. Let me clear the solution and try that again. There we go. Now it's plotting lift and drag. Against iteration. So as it runs more iterations, you can see these lines rapidly changed in the beginning and then are still changing but are slowly converging. So you can create one plot from multiple things, or you can create a single plot for each thing. It really depends what you're plotting. Does it make sense to plot a whole bunch of temperatures on the same set of axes? Probably. Whole set of velocities, forces, potentially. It depends. Plotting lift and drag on the same set of axes might not be the greatest thing in the world, depending on what you're trying to do. But you can also plot quantities against each other. Let's see here. We can plot. Let's see here. Data series. Add data. Where did that go? Well, we'll circle back around to that a little bit later. This is a little bit more fancy, but you can plot quantities against each other as well, if you so wish. It just gets a little bit more complicated. Oh, we want a monitor plot. That's what we're after. So if we add data, we can look at drag and lift monitors. And oh, we can plot. Let's do lift on the x-axis And then we're going to plot drag against lift. And we can see that this is what this trend looks like. Now that's not the most useful thing in the world, so let's go maybe plot something. Well, it doesn't make a huge amount of sense here, but yeah, we'll go ahead and do this. So just by kind of eyeball metric, I'm going to plug in reference values for this. These aren't particularly accurate reference values. They're close, but not quite. And we're going to look at the CL on the wing. Oh, nope, that's CD. 0 space 1 space 0. Now it's CL. There we go. CL of 1. We could copy this, rename it CD, and make it in the X direction. Now that's coefficient of drag, and that's drag. So we can create a monitor and a plot for CL and CD. Let's run a little bit more. So I'm going to clear the solution really fast just so we can see how this changes. And we're going to create a new plot, a new monitor plot. So this plots two monitors against each other. We're going to plot, let me see here, CL against, or CD against CL. So this should theoretically plot something that looks vaguely like a drag bucket. Well, in theory. In actuality, it probably won't because we're only looking at one angle of attack. But we can see this little line right here, it's slowly kind of figuring out what is our CL versus our CD. As it iterates over the simulation. So we're plotting quantities against each other. You can do a couple different things with plots, but the basic ones are mostly just plotting quantities against the iteration to see how your simulation is converging. We'll talk a little bit about how we use these in the future. However, where things get a little bit more complicated are scenes. Let's flip back into a slightly different mode and talk about scenes. So scenes are a little bit interesting because the way they work is a little bit non-intuitive. The first thing is that the scene is basically just this window that we're viewing the space of the simulation through. This window. We can create a new empty scene and see that it's just an empty window with only a couple things in it. It has an annotation at the top with STAR-CCM+, and it has a axis. So you can tell where you are oriented in three-dimensional space as you look at this thing. You can see I can kind of left click and pan around, and you can see that axis spin around. And you can control click and rotate it. A scene is just the window through which you are viewing space. You can create several types of scenes by default. You can create a geometry scene, a mesh scene, a scalar scene, a vector scene, or an empty scene. The only difference is it kind of auto-populates these windows, these scenes, depending on the type you choose. If you choose empty, it doesn't auto-populate it at all. If we want to see anything at all, we need to add a different thing to this scene. So we see where here we can see where it says scene 1 here, and we get a bunch of options if we right click on it. The important one is new displayer. The way we see anything in a scene is with a displayer. we have several different types. A surface displayer will simply show you where a surface is in three-dimensional space. So let's make a surface displayer really fast here, and we can see that it has a whole bunch of properties. A whole bunch of properties. The big one that we're going to care about is perhaps the opacity. You can make it partially transparent if you wanted to. We can't see anything yet, so that doesn't really do anything. But you can change its opacity. You can hide or show a mesh on the surface. You can hide or show its outline or feature lines. Or you can hide or show the surface itself. So if you wanted to just show the mesh without the surface, you could do that. If you wanted to just show the outline and nothing else, you could do that. You could do a whole bunch of different things. But noticeably, it doesn't have a property to tell you what surface to show. We need to look a little bit deeper. You see how there's this little tiny caret up here on surface 1? Well, we can see here that if we expand that, we get a parts folder. This is where we tell it what we want to show. In this case, I'm going to say, I want you to show me the surface of the wing. Well, it's two-dimensional. It's a two-dimensional simulation, so the surface of the wing is actually a line, rather than a full wing. If we wanted to look at the full wing, we could go back here and select the surface of our airfoil. And because this doesn't actually have a mesh on it, because it's two-dimensional, or sorry, this is three-dimensional and our simulation is two-dimensional, I needed to change this representation from latest surface and volume to geometry. But we can see that it is showing us, an important part here is that it's showing us the surface with this very original surface mesh attached of our wing. We could also ask it just to show us the mesh. It's no longer showing us the surface, it's showing us a wireframe mesh of what this wing looks like. We could ask it for an outline where it shows us every edge, but there's only really one sharp edge on this airfoil, and it's the trailing edge. So we see not quite a straight line, but almost just a straight line. This is the back surface of that airfoil. We look for feature lines, we get the end caps of the wing, or we could ask it just to show us the surface. And we can ask for this to be transparent. So now we can see through it a little bit. We can definitely see the far side through the wing with opacity 0.5. So this is the surface of our wing. That is a surface displayer. An outline and a mesh displayer are very similar. They just have different things selected by default. You notice how we can select or deselect mesh, surface, and a whole bunch of other things. Well, that's the only difference between these displayers. The surface, the outline, or the mesh, it just shows you different things by default. It's still a surface displayer. And you don't just have to show one part. You can show multiples. What if we want to show every part of our domain? And I think I accidentally selected something else. Oh, no, I didn't. I know what happened. If we want to show every part of our domain, we can select, well, everything and see all the boundaries on our region. This isn't particularly useful because it's a two-dimensional domain and it works a little bit weirdly, but we can indeed do this. So let's go ahead and just make sure nothing is selected. Okay, and we have an empty scene again. We could also create a new scalar displayer. Oh, sorry, I selected the wrong thing. Oh, let me hide that. There we go. Let me just get rid of that. There we go. If we want to plot a scalar quantity, you guessed it, we use a scalar displayer. So that lets you select a thing to look at the properties on. We can look at just the properties along our wing, or we could look at the properties. 1 second. Well, we need to tell it what property we want to look at. So where you see how it says select function, that means it's not actually plotting anything. If we want to tell it to plot something, we can click on this and select something. Let's select static pressure. And we can see that, hey, the surface of our airfoil is faint, but it's a thin colored line related to the static pressure on the surface. We could also change this by looking on the left here where it says scalar field, and we can change some properties, the minimum, the maximum, the units, a couple things like that. But we can also select the entire domain. Again, if you click this repeatedly until you get just the big box, it will plot everything in the domain. Align this so it makes a little bit more sense. So right click will pan, control click will rotate, control left click will rotate, or just left click hold will rotate about whatever point you click on. Or rotate in three-dimensional space, rather. Control click will rotate about the normal axis to the screen. So we just plotted static pressure on the entire domain. So the part is the entire volume. We are plotting static pressure. We could plot anything else we wanted to. We could, it's not going to be particularly useful, but we could plot temperature. Oh, hey, look, it does change by a couple of degrees due to pressure changes. Right, because pressure, temperature, density, they're all coupled together. It's not by much, but it is changing a little bit. Especially where the lowest pressure, the flow is expanding a little bit, temperature is dropping. You get some minimal compression heating on the front. Very minimal, according to this. We could also plot, let's see here, velocity, but velocity is a vector quantity, so we can't plot the direction, but we can plot the magnitude. So here's our vector, our velocity magnitude in the entire domain. Again, we can change the min max. If we only wanted to plot from, like, let's say 10 to 70, it will show us where the flow is between 10 and 70, or it'll show us everything else as well, unless you turn on this clip value. So clip will not show it if it's outside of this range. Clip off will just show it as the maximum value. Don't worry too much about that, but the point is we can change the min and max value that it's plotting. Now, one important thing, because this bar can be hard to read by default, is you can change pretty much everything about this. You can change how many different color levels does it have. Does it have 32 like it does now, or do we want 128 color levels along this bar? Do we want to change it to a bold italic font instead of whatever it was by default? How wide do we want it to be in fractions of the view window? Do we want it to be 30%? Oh, sorry, 0.3. Do we want it to be 30% wide? Do we want it to be 70% wide? Do we want it to have a background? In this case, a white background. Do we want it to have a shadow? I believe the shadow only matters if it has a background, or if it doesn't have a background. But do we want it to have a shadow? Do we want to reverse the color spectrum? Do we want red to be low and blue to be high? We can do that. The text position, whether it's above or below. How high is it? Do we want it to be 5% of the window? Do we want the title to be taller? Do we want the title to be 5% of the window? Label height. Maybe we want it to be 8% of the window. Really big labels. We can do that. Do we want it to be vertical instead of horizontal? Oh, that was not intentional. We can do that as well. Where is it located in fractions of the window? Well, do we want it at the very corner? We can plug in 0, 0. Doesn't work very well, but we could put it there. Or we could put it at 0.2, 0.2, or anywhere else we care to. Is it visible? Maybe we just want to hide the color bar. Is it a linear scale or a log 10 scale? Is the text black or is it, I don't know, the brown, green, like teal, turquoise? Is it opaque? Maybe we want this to be a transparent color bar. And you can mess with how many significant figures and other things you have. So this gets a little bit complicated, but this is a printf style format string. So you can, if you look up, what is it? D, I think, is printf. I forget. It's been a while since I programmed anything. But whatever the printf style you want to use is, you can use it here. You can look up printf and the arguments and how to format that, and all kinds of other things. And you can choose how many labels you want. If you want like more labels, you can make 5, 6 labels, less, more, etc. But you can choose everything about the color bar in the color bar. You can control the scalar field range itself here. If you want to just auto range it again, you can set it to auto. You can do all kinds of things with the scalar field, the color bar, just by manipulating this. And the last thing is we can, well, for starters, we can just hide, I believe, the entire thing by double clicking on it. So I can double click on the little icon next to scalar 1 and hide the entirety of scalar 1. The last displayer we're going to talk about today is vector. Now, a vector is very similar to scalar, except it displays a vector property and how it varies in space. Well, how do you display a vector? Well, you have to display its magnitude and its direction. By default, it does this with a whole bunch of arrows. The length of the arrow corresponds with the vector magnitude, and the direction of the arrow corresponds with the direction. It gets a little bit hard to see what the hell's going on, because you can see there's so many arrows by default that it's basically useless. You can control all the size of this arrows and things like that by looking under this glyph folder. So if I want to say only every 10 cells has an arrow, I can change the geometric spacing to 10. Better, Maybe only like every 40. A little bit hard to see, but there's kind of an airfoil in there now. You can see the high velocity over the leading edge. And because there's so many more cells here near the airfoil, we still really can't tell what's going on over here. But we can tell what the flow is doing out here. We could make the glyph length longer or shorter. Maybe we want really small glyphs. Maybe we want 1%. That'll make them smaller. Hey, there's our airfoil. But this is one way to show vectors. You can sit here and tune the properties of these. Maybe you don't want it to be geometrically spaced. Maybe you only want so many on the screen. Maybe you want the length to be constant. Maybe you don't care about the magnitude. You just care about the direction. Should the vector scale be an absolute value? Should it be based on the part size? Should it be based on the screen size? Should it be direct, which is specified in a dimensional size according to space, I think? So by default, 1 meter. That's a little bit long. Now they're 1 millimeter. Those are probably a little bit short. I still don't know where our airfoil is, but it's somewhere. But you can specify a great many things about how big those arrows are with this setting. Let's see here if we do part size, screen size. There we go. You can also change whether it's like a 2D wireframe, 2D filled head, whether it's three-dimensional in nature, etc. Whether it's a cone or maybe a sphere. I'm not quite sure why you'd want to plot a sphere or use spheres as a vector, but you know, more power to you. You can change a whole bunch of things about these arrows if you do this. We still have all of the color bar options that we had before. I'm not going to go through them again. They're the same. We can choose what property we want to plot. Maybe we just want to plot position. Well, it's not particularly informative, but we could plot it. We could also plot, let's see here, vorticity. Well, that seems to be rather small, actually. Let's do like 5. Let's change the max value to something a little bit smaller. Nope, we seem to have lost where our arrows are. So this brings up an excellent point. We can kind of unlose ourselves because we can have more than one displayer up at once. Maybe we want to show what this part looks like or what our wing, where our wing is. Ah, there's our wing. Still can't see any of the arrows. They're there very, very faintly if you look real close. Hey, look, there's some vorticity arrows. But you can plot any vector quantity you want this way. Some of them make more sense than others, but you can plot any vector quantity you want this way. I'm going to set it back to velocity because that makes the most sense for us today. But you can plot these arrows in many, many different ways. Getting them just right can be a little bit of a pain, though. So there's another way of plotting vectors that doesn't involve these arrows. And it involves changing, if we go up to this vector displayer, it involves changing the display mode. There's other options you can change here as well. Display mode is kind of the big one. We can change it from glyph to line integral convolution, which plots it looking like this. I think this is a lot more useful personally because it does show you the direction. You can see these little like snow hash marks, static marks. It shows you the direction and it shows you the magnitude. It does it in a much more uniform way. It does it in a much, in my opinion, more intuitive and more importantly, more foolproof way. Like this is rarely going to look bad or very rarely going to be hard to read. Um, and you have all the same properties that you can mess around with, except for the arrow ones, right? You can change, for example, what is this? Let me see here. 20. We can smooth it out by changing the number of steps. The blending factor, you can make it smaller, larger. You can tweak how this looks as well. Like, do you want it to kind of have more of a staticky appearance? Turn down the step size. That looks more staticky. If you want to be more blended, you can turn up. Oh, maybe not that far. 0.9. The blending factor is contribution of the LIC in the final image. Well, clearly the blending factor works the opposite way that I would have thought logically, but oh, it's how obvious the little snow marks are. So if you turn this to 1, the snow marks are literally everything. If you set this to 0.1, you can barely see the little hash marks at all. If you set it somewhere in the middle, you can see the hash marks pretty well as the color field underneath. The number of steps is basically how much effort does it spend in integrating each one of these little hash marks. So you notice the hash marks get longer. You look really close here. The hash marks sort of get longer as we crank up the number of steps, or they get shorter as you turn it down. I think the default was about 20. And I would leave enhanced on by default because that's what it looks like without it. Kind of snow, honestly. Like you can still kind of see the direction, but turning on enhanced I think helped a lot. So again, we have several different ways to look at things. We can look at surfaces or geometric definitions with a surface displayer. We can look at scalar quantities with a scalar displayer. We can look at vector quantities with a vector displayer. And we can look at them in any combination, right? We can look at a surface and a vector displayer. Absolutely. It doesn't make a huge amount of sense in a 2D case, but we can look at other combinations of things as well. I'll have to show you a good 3-dimensional case where streamlines are really important, but we'll get to that a little bit later. But rather we want to look at static pressure, temperature, dynamic pressure, total pressure, velocity, density, you name it, we can look at it. And if you want to save an image of any of these scenes as they're not quite as they're shown, but close, you can right click on these and say hard copy or hard copy to clipboard. If you hit hard copy, it'll ask you, where do you want to save this? What resolution do you want to use to save this? Do you want it magnified or not? Should the background be transparent? Or you can right click and say hard copy to clipboard. And paste it to the clipboard. Controls, it's effectively the same thing as control scene or doing a partial screen capture the good old fashioned way. It's a little bit more robust because Star actually knows you're doing it. So hard copy or hard copy to clipboard are good ways to, that's what I'm looking for. Good ways to export these scenes from STAR-CCM Plus. So by default, usually the resolution it will use is the same resolution that's currently being displayed at. So since this occupies most of a 1440p display, but not all of it, it's a little bit larger than a 1080 display, or it's slightly smaller in the Y direction than a 1080 display, but it's wider because the aspect ratio is wider. So it'll use the same resolution as the window you have up by default. Or you can lock the aspect ratio, and let's see, if we wanted this to be exactly 1080 wide by whatever, or we wanted it to be 1920 by 1080. We want it to be a full screen screen capture. We could do that. There we go. Full screen capture. At the resolution where if we looked at it in full screen, it occupies, well, what would be a 1080p display, except it's shown on a 1440p monitor. So I think that just about does it for this one. I'll go ahead and wrap this recording, and we will talk again during class.